So we're beginning our work today by starting to integrate some of those thermodynamic concepts into electrochemistry. So yesterday was almost exclusively about the reactions themselves and the electrical energy that they produce. Well, what we can build off of this is that there is a direct relationship between the measured voltage of that cell and the work done by that cell, which is the free energy of the cell. And the relationship between the two is that delta G, the free energy for the cell, aka the work done by the cell, is equal to negative Q, Q being the electric charge in coulombs, times the measured value of the cell potential. And the reason why that works is because when we measure something in volts, the volt is a combination unit, is the combination unit of joules, the standard unit of energy, and coulombs, the standard unit for charge. And so volts are joules per coulomb. So if I multiply my volts by the number of coulombs of electric charge that are being moved, transferred, I would get the amount of work or the free energy. And the negative value there is because Q, the electric charge, can only be positive, and we associate spontaneity with a positive E value. So if we are going to get a spontaneous response from delta G, we have to add that negative term to get, because spontaneous processes would be positive for both of those terms. So we have to take the opposite of them, which also means that if we have a non-spontaneous reaction cell, a negative E, that would also give us a positive delta G, which is exactly what we would expect. Now, we can modify that idea of work by looking at a slight variation. So instead of capital Q, the charge, what we're going to do is we're going to break that term down into some more attainable pieces. And that's where this equation comes in. And this is the most familiar form of the relationship between delta G and E. Delta G is equal to negative NFE. N being the number of moles of electrons transferred in the process. And for that, you would need to have your balanced redox reaction. F being Faraday's constant, 96,485 coulombs per mole of electrons. This gives us a definitive charge per mole of electrons. And so if I multiply N and F together, that gives me that value of Q that we were looking at in the previous problem. And so this equation is basically another way of determining the work done by the cell. And we're going to use this form because it's a lot easier to deal with. It's a lot easier to look at the balanced chemical equation, look at the redox, the oxidation numbers, and determine how many electrons are moving around. Faraday's constant is a constant value, so we don't need to worry about it changing. Cell potential is easy to measure using a voltmeter. Now, if we happen to be at standard conditions, and just as a reminder, standard conditions are 1 bar of pressure, which we can easily estimate that's just slightly better than 1 atmosphere. 1 molar solutions. And 25 degrees Celsius. If we're at those conditions, the equation is exactly the same. We just get to call it standard free energy change and standard cell potential. But the calculation process would be exactly the same. In fact, everything would be exactly the same except for the value of E versus E naught. This value of E naught, the standard conditions, we can get that using the reduction potential tables. This value of non-standard E, we would have to measure it experimentally. But it gives us that option. Now, what this also allows us to do is by incorporating this relationship with our other thermodynamic relationships, we get a series of equations that we can easily go between to look at different kinds of calculations. So we already know from our previous slide that delta G was equal to negative NF E. Well, if I rearrange that and get E on the one side, I can use this equation, substitute RT natural log of K, and I get this equation here, which gives us a relationship between the cell potential and the value of the equilibrium constant for that particular substance, or for that particular reaction rather. And obviously the more reactant favored it is, the lower the value of E is going to be. And the more product favored it is, the more favorable E is going to be. And so we can easily interconvert between these 3 thermodynamic parameters and equilibrium parameters by using different manipulations of the equations that we already know. So we already knew from chapter 12 the relationship between delta G and the equilibrium constant K. We just saw the relationship between delta G and the standard cell potential E. And now we can see that by rearranging those to each other, we can determine the relationship between the equilibrium constant K and the standard cell potential. Again, this is all useful information to us because, like I said at the end of yesterday, we're coming to the point where we're stitching this all together and putting the thermodynamic stuff fully together with the equilibrium stuff, which really means that over the course of this entire semester, everything is kind of related to each other with the exception of kinetics, because kinetics brings in a completely different worldview. It's all about the speed of reaction, not whether the reaction happens or the extent to which the reaction happens. Everything else we've talked about is in that second category. We've just looked at way many different viewpoints for determining that. So let's take a look at an example problem. We have a cell that has a standard potential of 0.177 volts at 298 Kelvin. What is the value of the equilibrium constant K if n is equal to 1 or if n is equal to 2? So we are looking at the relationship between E and K here. Delta G is not in the picture. So we are going to use this equation. E is equal to RT over NF times the natural log of K. So RT over NF times the natural log of K. Now, the wonderful thing about these equations is that there are a good number of constants that are involved. R is a constant, F is a constant, and in our case, we're looking at two different versions of what happens at 298 Kelvin. That one's kind of a constant, at least in our circumstances as well. Now, you will see there are different versions of this equation that float around. And when we get to the Nernst equation in particular, we'll see a version of that where we say, okay, we do so much of this at 298 Kelvin, 25 Celsius. What if we considered that a constant as well? So what you'll see occasionally is if you take 8.314 times 298 divided by 96,485, you'll sometimes see equations like this. Where because we're working at standard conditions, they'll just integrate that temperature into the constant. And it's totally okay if you use an equation like that. It does simplify things, but it is not on this equation list. And it might not be on the list that I give you for your exams either. It's just one of those, you know, if you're doing your homework and they're all kind of beating on the same drum, you know, what are some ways to speed up the process a little bit without sacrificing accuracy? This is one of those kinds of shortcut equations. It's derived from here, though. So when n is equal to 1, we have 0.177 volts. It's equal to 8.314 joules per mole Kelvin times 298 Kelvin over 1 mole of electrons and 96,485 coulombs per mole of electrons times the natural log of K. Now, what we will see here is that everything's going to basically cancel out by the end of this. My moles of electrons cancel out, my kelvins cancel out. Joules per Celsius is volts. So by the time I divide this into the other term, the volts will cancel out the joules per coulomb. I'm going to be left with nothing, which is perfectly fine because equilibrium constants have no unit to them. So anyway, I do the calculation, 8.314 times 298 divided by 96,485. I get 0.177 volts is equal to 0.0257 volts times the natural log of K. Again, the volts here coming from joules divided by coulombs, that is by definition a volt. If I divide each side by the 0.0257 volts, I get 6.89 is equal to the natural log of K. E to both sides of that gives me a value of K equal to three significant figures, 980. So not surprisingly here, a spontaneous reaction is going to have a relatively large equilibrium constant. Now for n equals 2, we're going to use the shortcut equation this time, just to save ourselves a little bit of space and a little bit of our sanity. 0.177 volts is equal to 0.0257 over 2 times the natural log of K. So dividing each side by 0.0129. We get 13.7 this time. Which to three significant figures would be 9.1 times 10 to the 5th. So it's even more product favored with that second electron moving now as well. Which should make sense, because if we think of delta G as being equal to negative NFE, the more electrons that are moving through the process at the same voltage, the more spontaneous that process is going to be, the more favorable that reaction is going to be. And so more favorability means a larger equilibrium constant. So that should be no surprise there. Any questions with this example? If the equilibrium constant for a 2-electron redox reaction at 298 Kelvin is 1.5 times 10 to the negative 4th, what is the value of delta G and E cell? So since we have multiple equations here to use this, we have multiple ways to solve this. Now, for delta G, the most straightforward approach would be to use the equation delta G is equal to negative RT times the natural log of K. That one's kind of the most direct. And if we do that, negative 8.314 joules per mole Kelvin times 298 Kelvin times the natural log of 1.5 times 10 to the negative fourth. Would give us 2.18 times 10 to the fifth, negative 2.18 times 10 to the fifth. So delta G would be positive 2.18 times 10 to the fifth joules, or positive 21.8 kilojoules. Now for E cell, we could go a number of different ways. We could use that same equation. E is equal to negative RT over NF times the natural log of K, and get our E value that way. We could also use this value of delta G. Delta G is equal to negative NFE. So 21,800 joules is equal to negative 2 times 96,485 coulombs times E. $21,800 divided by 2, negative 2. Divided by 96,485 would give a value of negative 0.113 volts as the E cell for this process. Now, like I said, you could go the other way with it. You could do the E is equal to negative RT over NF, natural log of K route. Which, since we're at 298 Kelvin, would be using the shortcut here. You'd get the same negative 0.113 volts. Actually, I copied that equation wrong. It's positive RTNF. So method really doesn't matter here. That's why there are multiple equations. You just kind of, you pick the one that you're the most comfortable using, and you try to just make the best of it at that you can. Any questions with this? All right, here's one I want you to try then. There's quite a bit going on in this question. It's concerning an actual battery. It's a button battery, like the ones that you would put in a watch or a hearing aid, or something along those lines. and it's got a zinc anode and a silver oxide cathode that is surrounded by a base solution of potassium hydroxide. We know that silver oxide is reduced to silver and zinc is oxidized to zinc hydroxide at the anode. So we need to get the correct net ionic equation. And then with that net ionic equation, use the electrochemical reduction potentials in that manual to figure out the value of E cell, and then use the value of E cell to figure out the value of delta G. So two things going on here at the same time. Go ahead and start working on that. We'll take a few minutes. Come back and see how you did. All right, let's see how we did. So this problem had a lot going on for it. There were lots of different pieces and parts to it. You had to kind of set them all straight before you could kind of even begin to do the calculations part. So the first thing was we had to find the correct reactions. We were told in the problem that at the cathode, we had silver oxide turning into silver. We were told that at the anode, we were having zinc turning into zinc hydroxide. And this all had to be occurring in a base solution. And that was important in particular for the silver, because the transition from silver oxide to silver had a reaction for acid and a reaction for base. And there were different E values associated with each. We had to choose the right one. So these were the equations that you needed to end up finding. Silver oxide with water and 2 electrons makes 2 silvers and 2 hydroxides. The reduction potential for that was a positive 0.342 volts. And then the other one that you would find would have been the reverse of this. Zinc hydroxide plus 2 electrons makes zinc and 2 hydroxides. And the reduction potential for that would have been negative 1.199 volts. So the first thing we were asked to do was to find the net ionic equation, add all of this stuff together. And what we should have recognized upon adding them together is that the hydroxides canceled and our electrons canceled. Now, this piece here is important because it's telling us what our value of N is going to be. Now, it just so happened that they exactly canceled each other out from the table. If we had to do a further calculation, multiply this one by 2, multiply this one by 3, whatever the case would be, N would be the number of electrons being transferred after those manipulations. So if I have to multiply 2 electrons by 3 to get the electrons to balance out, that's 6 electrons. We would call that a 6 electron process. And so N would be equal to 6 in that case. So that being said, it worked out kind of in our favor this time. So the net equation is silver oxide reacting with water and zinc to make silver and zinc hydroxide. Now, the E cell value, we could use these reduction potentials, and that would be 0.342 volts minus the negative 1.199 volts. Which would give us 1.541 volts. If you chose to add the two equations together and add the potentials, you just had to remember that since we flipped this around, we would need to flip the value around as well. Before we added them. So that gave us our standard reduction, or excuse me, our standard cell potential. Now to turn that into delta G, we had to take care of the other equation in play. Delta G is equal to negative NFE. We already established N is 2 moles of electrons. The Faraday constant, 96,485 coulombs per mole of electrons. And our E cell, 1.541 volts. And remember that the volt is joules per coulomb. So the moles of electrons cancel, the coulombs cancel. I will get a delta G value here of -2 times 96,485 times 1.541 volts to 4 significant figures, because this 2 is an exact number. We get -297,400 joules, or -297.4 kilojoules. So the real nice thing about this interplay relationship between G and E and K is that once we know one of the values, it's really not that difficult to figure out the others if we have the balanced chemical equation at our disposal, if we know how many electrons are moving. If we don't, then we need to figure that piece out to calculate the others. But that usually comes as just a result of inspecting the equations themselves or evaluating the oxidation numbers and looking how they change. So you could look at this and say, okay, I see zinc is going from a 0 state to a +2 state. And there's only one zinc that's doing it. This must be a 2-electron process. All right, any questions? Okay, so we've done a lot of coverage on kind of these manipulations when we are at standard conditions. Again, standard conditions, 1 bar of pressure, 1 molar solution, 25 degrees Celsius. But the thing is, as these reactions proceed, they're eventually going to slow down. A battery doesn't go on forever. We all know that eventually the AA batteries in your Game Boy run out. And you got to replace them. Or if you have rechargeables, you've got to reverse the polarity and recharge the batteries. When that happens, when that battery dies, what we have in that circumstance is a value of E equal to 0. And we know that all batteries degrade over time. The battery fresh out of the package is a lot more efficient, requires a lot less shaking it up and thumping it against the table than the battery that is just barely hanging on and can, work for a little bit, but then it kind of stops working. So while our calculations to this point have been relatively straightforward and kind of working with ideal conditions, we know that those don't hold forever. If we sat there and did that electrochemistry lab and we just held it there for a period of time, we would notice that the voltage would start to decline over time as we were watching it. So other than this quantitative idea or qualitative idea of we know that batteries degrade, can we actually put some numbers to it? And of course, no question in chemistry is answered hypothetically. There's, of course, a way to do it. It's called the Nernst equation. Now, what the Nernst equation does is it allows us to relate the potential of a cell to the standard potential based on current conditions. The current conditions given to us by either our changing temperature condition, T. If we go at 25 degrees Celsius, it's at standard conditions. But if we go at, say, 200 degrees Celsius, it's at non-standard conditions. We expect to see some kind of change. And the relative amounts of Q are equilibrium conditions. And so the Nernst equation here gives us that relationship, says that the measured cell potential is equal to the standard cell potential minus RT over NF times the natural log of Q. And again, Q being the ratio of products to reactants in a reaction system. Now, the wonderful thing about the Nernst equation is that it works under all circumstances, even standard conditions. Because if we are working under standard conditions and we have 1 molar quantities of our reactants and products, well, it doesn't matter what the coefficients are. 1 times 1 times 1 times 1 divided by 1 divided by 1 divided by 1 divided by 1. The answer is going to be 1. And if Q is equal to 1, the natural log is equal to 0. And that whole half of the equation collapses. So at standard conditions, Q is equal to 1. This whole negative business here becomes equal to 0. The prescribed E is the same as the standard E. Now, one important application of that if you noticed yesterday, if you're paying close attention to the stuff that we were using, you'll notice we weren't actually collecting at standard conditions. We weren't using 1 molar solutions of all the metallic salts. We were using 0.1 molar. Now, the reason we were using 0.1 molar instead of 1 molar was because we could get away with it. And the reason we could get away with it is because if you looked at the equilibrium constant involved in those, what you would have found is that we basically had 0.1 divided by 0.1 as our value for Q each time. And so 0.1 divided by 0.1 is the same as 1 divided by 1. It's 1. And if Q is equal to 1, that whole side of the equation collapses. The measured cell potential is the same as the standard cell potential. And so we could get away with making lower concentration solutions, which costs us less money, and still get the same results because the reaction system basically gives us the same thing. And so that's an important distinction to make, because what that really tells us is that if we can maintain standard temperature and pressure, depending upon our reaction itself, we don't necessarily have to obey standard conditions in terms of concentration. The Nernst equation tells us so long as our Q value hits uniformity, singularity, Q is equal to 1, it'll be like we were conducting it at standard conditions anyway. Now, like I said before, you will see that if we are talking about 298 Kelvin, a lot of textbooks will offer you that shortcut equation of the Nernst equation, where if we are at 25 Celsius, we can pull out R as a constant, T as a constant, F as a constant. And for some reason, and it's gotta be, it's just an old school way of doing things. Before better calculators existed, log base 10 was a heck of a lot easier to deal with than natural log. That's really the only explanation I can come up with for why the natural log gets turned into a log in this particular case. But that's what you have. And so the book offers this modified version of the Nernst equation, and you are certainly free to use it if we are at 25 Celsius. Now, if we're not at 25 Celsius, you have to use that top equation instead. Let's take a look at an example. Here I've got a voltaic cell that uses this equation reaction at 298 Kelvin. What is the cell potential under standard conditions? What is the cell potential under these stressed conditions, where we've got 3 molar nickel and 0.1 molar zinc? Well, we've got to find the correct equations. So we know that the one equation is zinc ion turning into zinc. And we know that the reduction potential for that, because we've seen it several times, is, I'm going to look it up anyway, negative 0.761. And the other one we got to look for is the nickel ion turning into nickel metal, and the reduction potential there. Is negative 0.251. So we can see from the equation itself that the nickel is the cathode and the zinc is the anode. So for number 1 here, our standard cell potential would be negative 0.251 volts for the nickel minus negative 0.761 volts for the zinc. which would give us 0.510 volts as our standard potential. For the second, we need to use the Nernst equation. So E cell is equal to E naught cell minus RT over NF, natural log of Q. Our standard potential was 0.510 volts. We start plugging in all of our values here, 8.314 joules per mole Kelvin. Times 298 Kelvin divided by, this is a 2-electron process. So 2 moles of electrons times 96,485 coulombs per mole of electrons times the natural log of Q. Our Q value here is products over reactants. The product here is zinc. So 0.100 divided by the concentration of nickel, 3.00. So a lot going into this one. 0.1 divided by 3 is negative, or excuse me, is 0.033. So the natural log of that times 8.314 times 298 divided by 2 divided by 96,485. What we get is that the non-standard is equal to 0.510 minus a negative 0.0437 volts. So in total, 0.554 volts. And this makes some sense, right? We've got a condition that is clearly more reactant favored because we've added so much extra nickel relative to the product. And so that's going to push the reaction toward the products, which would increase the voltage. So like we were talking about yesterday in lab, this is basically Le Chatelier's principle. I decrease the concentration of the product, or I increase the concentration of the reactant. It shifts to accommodate that. A shift toward the products in this case would cause an increase in voltage. Any questions? All right. Here's another similar kind of problem. We actually did a version of this yesterday. What is the value of E cell at 25 Celsius when copper concentration is 0.1 molar and the zinc concentration is 1.9 molar? The standard potential is 1.104. So we already have kind of the marks here for a start. We can calculate our value of Q. Our value of Q would be the concentration of the zinc, 1.90 molar, divided by the concentration of the copper, which would give us 19.0. So E is equal to 1.104 volts minus 8.314 joules per mole Kelvin times 298 Kelvin over 2 moles of electrons. Because again, even though I don't have the values I can track, zinc's going from a 0 state to a +2 state. That must mean that 2 electrons are being transferred. 96,485 coulombs per mole of electrons times the natural log of 19.0. So if I put all of that in, E cell is going to be equal to 1.104 volts minus whatever the combination of products here is, 8.314 times 298 times the natural log of 19 divided by 2 divided by 96,485. I get 0.0378 volts. Which rounding to 3 decimal places would give me 1.066 volts. And not surprisingly, we saw this exact thing in lab yesterday. We had a higher concentration of zinc compared to copper when we poisoned the copper cell with ammonia. And we saw a drop in the voltage as a result. Now, this should give you a little bit of insight into just how far we dropped that copper concentration when we poisoned it. Because this is a 19-fold difference in the concentrations, and it barely moved the voltage. Yet you saw yesterday a pretty significant dip in voltage, what, about 0.3, 0.4 volts almost. So that just gives you an idea. We had 0.1 molar zinc. How far did that copper concentration have to go to give us that big of a drop? Considering that pretty much everything else about this reaction was exactly the same. We did it in the lab. The lab's like 24 degrees instead of 25, so that's not going to make that big of a difference. It's the same exact equation, but the disparity in concentration had to have been really significant. All right, any questions with this example? Okay, so we're going to end this first portion of the lecture today talking about an application of the Nernst equation. And this was something I showed you in lab yesterday. It is possible, using the Nernst equation, using the fact that we have non-standard conditions, that you can actually make something called a concentration cell. A concentration cell is simply a voltaic cell where both electrodes are exactly the same, at least in terms of their composition. So yesterday I showed you a copper concentration cell where we had copper electrodes in both solutions, and we had 2 different solutions of copper to sulfate, I think it was. And the 2 solutions, the difference in their concentration was enough that at standard conditions, a copper electrode attached to a copper electrode should give us 0 volts. But when I introduced a non-standard copper solution, we picked up like 0.3, 0.35 volts out of it. And that's how this kind of thing can work. Current can flow from one cell to the other, so long as there is a difference in their concentrations. But keep in mind, as the reaction proceeds, the more concentrated solution is going to get less concentrated, and the less concentrated solution is going to get more concentrated until they meet in the middle again. And when they meet in the middle again, voltage goes back down to 0. So let's look at an example here. We have a voltaic cell made with 2 hydrogen electrodes. Electrode 1 has the pressure of hydrogen at 1 atmosphere, unknown concentration of hydrogen ion. Electrode 2 is the standard hydrogen electrode with a 1 molar solution of hydrogen ion and a 1 atmosphere pressure. At 298 Kelvin, the measured potential is 0.211 volts. And we see the electronic current flowing from electrode 1 to electrode 2. What is the pH of the solution? So what this tells us, since the electricity is going from 1 to 2, that means that the electrode 1 has to be the anode and electrode 2 has to be the cathode. And the reason why that is important is going to be because that's going to help us to figure out what our equilibrium looks like. Because on the surface, we're not going to get a whole lot of the balance out of the balanced chemical equation. Because the balanced chemical equation appears to be identical on both sides. But with this information about which one's the cathode and which one's the anode, we can get a little bit better information. At the cathode, we would see the hydrogen ion turning into hydrogen gas. Because remember, reduction occurs at the cathode. So a +1 turns into a 0. That's reduction. That's got to be our cathode. Which means that the hydrogen has to turn into hydrogen ion at the anode. Now, since we have identified the cathode and anode, we can now identify which electrode is which. And apply the appropriate values. So the hydrogen ion in the reactants is the standard hydrogen electrode. That's a 1 molar solution. And we're going to ignore the differences, slight as they are, between 1 atmosphere and 1 bar for the purposes of this problem, because it really wouldn't make that big of a difference. And for the anode, we also had 1 atmosphere, but we have an unknown concentration. As far as our Q value is concerned for the Nernst equation, it would be the concentration of the hydrogen ion in electrode 1 squared times the pressure of the hydrogen in electrode 2 divided by the concentration of the hydrogen ion in electrode 2 squared times the pressure at 1. Well, since most of those values have been determined for us, the only one we don't know is the value of the hydrogen ion at electrode 1 squared. Everything else, this was 1 atmosphere. This is 1 molar squared. This is 1 atmosphere. So the pressures cancel. 1 squared is 1. Whatever value we get for Q is going to be equal to the square of the concentration of the hydrogen ion. So that's what we need to keep in mind as we're evaluating the Nernst equation here. Nernst equation says we got a potential of 0.211 volts. Since this is a concentration cell, our standard potential would be 0 because that's the same reaction, front ways and back ways. And just to add insult to injury, the standard reduction potential for both of those is 0 because it's the standard hydrogen electrode. So solving for the natural log of Q, because since this 0 term is 0, we can just kind of move it out of the way. 0.211 volts is equal to negative 8.314 times 298 divided by 2 divided by 96,485. So if I do my algebra here, 0.211 times 2 times 96,485 divided by negative 8.314 divided by 298, I get negative 16.4 as the natural log of Q. So raising that to E, that gives me a Q value of 7.3 times 10 to the negative 8th, which is equal to the concentration of the hydrogen ion squared at electrode 1. So the concentration of the hydrogen ion at electrode 1 would be the square root of that, which would be 2.7 times 10 to the negative 4th molar. So with these kinds of calculations, I mean, there's a lot that it takes to get there. There's a lot of calculation steps. But the good news here, if you want to look at it that way, is that it really just falls into the purview of algebra. You just got to make sure that you've got your algebra good and tight. And if you do, it's hard to make mistakes. If you don't, you can run into some problems there. Any questions with this concentration cell problem? Because 1 squared is equal to 1. So basically, I canceled all of that stuff out because they all ended up equaling 1. And so since it was hydrogen squared times 1, I just reduced it all. Now, if it wasn't 1, if it was something else that we knew, let's say that it was 2. And so we ended up having the hydrogen ion squared divided by 2 squared. All that would mean is that I would just take this as Q is equal to H squared divided by 4. I'd multiply by 4 before I took the square root. That's really the only thing I would do differently. But since it was 1, we could kind of just factor it out because it's 1. Other questions? All right, I've got one for you to try then. We have a silver concentration cell made by taking a 1 molar silver solution in cell 1 and an unknown silver solution in cell 2. The measured voltage is 0.26 volts. What is the concentration in cell 2? And just to clarify things, we're going to say the same thing that we said in the first one. Electron flow is going from 1 to 2. That way you know how to set up your value for the equilibrium constant. So take a couple minutes, chew on this one for a little bit, and then we'll see how you did. All right, let's see how we did. So similar setup to this one as the last one, where we need to figure out which electrode is which. Now the value of Q is a little bit easier to come by because there aren't as many components. It would be the concentration of silver at electrode 1 over the concentration of silver ion at electrode 2. No squares, no silver metal to contend with, just those 2 concentrations. And if we go back to the problem itself, we can see that cell 1 had the 1 molar solution. And we're trying to figure out the solution concentration in cell 2. So this sets up slightly differently. Our Q value is going to be equal to the reciprocal of the concentration of the silver ion. Since this was a 1 molar solution here. But we would go about it pretty much the same way. We start with our measured voltage, 0.26. So 0.26 volts is equal to 0 volts, because again, this is a concentration cell, so a silver cell shouldn't transmit any electricity to itself. Minus RT over NF, so 8.314 joules per mole Kelvin, 298 Kelvin. This is a 1 electron process this time, though. It only takes one electron to go from silver to silver ion. So if you made the assumption that it would be 2 because it's been 2 every other time, that was a poor assumption to make. You're going to end up with a slightly different value for the concentration. Once again, the 0 value here, we can kind of just ignore. So to find the natural log of Q, we just need to move everything around. So 0.26 multiplied by 1, multiplied by 96,485, divided by negative 8.314, divided by 298. We get that the natural log of Q is equal to negative 10, which gives us a value of Q at 4.0 times 10 to the negative 5th as the concentration, the reciprocal of the concentration of the silver. So I need to take the reciprocal of that to find the concentration of silver. And I'm going to get an extremely insane number. 25,000 molar as the concentration of the silver ion. So what does that tell us about our assumption? Well, what it should tell us is this is impossible to do. And the reason it's impossible to do is because we've got the electrons flowing the wrong way. If the electrons were flowing from 2 to 1, then this would work out. And instead of needing a 25,000 molar solution, the value that we found here, 4 times 10 to the negative 5th, that would be the concentration of the silver ion in cell number 2 if the electrons were going the other way, from 2 to 1 instead of from 1 to 2. So all that is to say, it's hard to do things a certain way. You're going to run into limitations. If you are dead set on electrode 1 being the anode, then you, or excuse me, electrode 1 on being that anode, then you've got to have a really concentrated cathode. And 25,000 molar is beyond the limitations of concentration. You'd either have to lower the concentration in the anode or in the anode so that you could lower the concentration in the cathode accordingly. All right, any questions with this example? All right, let's take a 5-minute break, come back at 5 after.